Today I will show you how we can utilize a hybrid optimization technique for finding the reduced order model. So for today's video is I have got this optimization technique, that is hybrid of Gray Wolf and Cuckoo search optimization algorithm. This is the optimization technique that I downloaded from internet, and the reference paper for this optimization technique is also there. You can download. I will share that link to you in description of this video. So first I will do extract. I will extract these files, and here this is the thing, right? So what I will do, I will just cut and paste it to some other location. Like this is my location, and I can write it like hybrid GWO and CS, and this I'm doing it for model order reduction. Okay, so before proceeding, what I have to do, just change the directory of this MATLAB. Okay, good. So in this too many files are there, we have to start with this file, main file. So first I will open that editor window and just simply check this. Yes, so this is the editor window, and if we want we can change the function name, and for simplicity I'm running it for 50 iterations only, just to show how it is working. Okay, so by pressing F5, change this folder, can run the simulation, and after completion of this simulation we'll get the output. So this is the function that we have given input to that optimization technique. Fine, and this is the iteration graph that we got. Means in this GW and GWCS has been compared. Okay, so what I will do, right, so basically this is some other function, and this is some square function basically, right? But we have to find the transfer function, I mean reduced transfer function for the any of the higher order system. So I will make changes in these codes only, and I will show you what are the things need to be changed. So first I will just modify some these files. Okay, it's good. And for the initial start I will run for this 10 second, and I will just make changes in something. So okay, good to go. So and now what I will do, if you see here, this is the function right now selected as F1. So where that function is, this function is inside this file get function detail, because here only it is asking for function name. So all codes are interlinked basically. This is for clearing the screen and closing all the windows, that is figure windows and all. And this is the search agents, like total number of population you can say in like in PSO, and this is the maximum number of iteration. And here right now function F1 is selected, so this function is going inside this get function details. So what I will do, I will just open this first, so we can see miss what is the things inside that function. So if you see here, this function is selected right now F1, and here upper bound and lower bound is given as minus 10 and 10, sorry, minus 100 and 100. So but in our case I will try to use lower bound as minus 5 and upper bound as 5. And so means I will tell you the problem. In our case I have got one transfer function of the fifth order, and we try to find the reduced model of the second order. So in second order, a standard form of like transfer function is means in denominator we will have 3 terms, in numerator we will have 2 terms. So 3 plus 2, total 5 variables we need to find. So this is what I did. I mean the range of that variable would be minus 5 to 5, and the total number of variables that we are looking for is 5. So after that we need to change the objective function. I mean what is our objective? So this right now this is the function that is being used for minimization. I mean sum of a square, means basically it's a square function, you can say circle function, right? Circle, it is trying to reduce that circle. So what I will do, I will just delete this. Yes, and here I will write our own code, own set of code to define the original system and to define the reduced system. So I will start writing. This is original system, and this I can define like numerator is equal to 1 7, 24, 24. This is a standard transfer function that you can get from many of the paper, and denominator is equal to 1, 10, 35, 50 and 24. Okay, so now I will form transfer function g1 is equal to transfer function numerator comma denominator. So fine, and I will suppress the output. I can comment it like original system transfer function. In similar way, I can define that reduced system also, reduced system, but a reduced system will be defined in terms of variable, because we try to find that variables values or coefficient using these techniques only. So what I will do, I will define here, if you see this argument is x1, so I have to define reduced system in terms of that only. So for numerator thing, I will write it like nr, and I will define like x1. So in numerator we will have two terms, x1 and x2, and denominator will have three terms. It's a standard transfer function for any second order system, x3, x4 and x5. Okay, so and I can form transfer function as similar to that, numerator comma denominator. Fine. Okay, now I have to assign this time for which we want to run our simulation time. So tsim will be 10 second I am taking. Now I will discretize the time instant. So dt will be something 0 to 0.01 and this tsim. Okay, so after that what we will do, we'll have to find the, basically in model or reduction we try to find the transfer function that will replicate our original system. Basically it should look similar to that of original system response, and if I say that it should be similar to that step response, body plot, whatever. So what I am doing here, I am considering error between step responses for finding the transfer function. Basically this optimization will compare error between two step response. One is for original, that is g1, and other is g2. So it will plot these two response and try to coincide these two by changing the variables of g2. So what I will do, I will try to find the error first. Error means between step response. So both response will be subtracted. Then that is called the error. So basically step, and this is our g1, and this will run for dt time, right? Minus step g2 comma dt, right? So this will calculate the error, and what I will do means, in this I am considering IAC as an optimization function. So it should be like integral square error. So means that error should be squared. So how this can be squared? So this can be squared by simply taking this square element wise. This dot is showing element wise square, and after that what we have to do, just we have to integrate this term like trapezoidal, trap z, and trapezoidal is asking one time instant, I mean dt, like integration of x dt. So dt, that dt is this one, and this is our x means, I mean function, this is the function. Fine. So okay, good. And this is giving output to O. So what I will do, I will store this to O. So this is done. Okay, good. So what I will do, I will try to find something. And one more thing, now I am not using this like function parameter space, because I have changed our function. So this won't be helpful for us, and this also we don't need. We need only the graph. So this will be our iteration graph, and this I will plot in figure 1. Good. And I will see once, and if I go this side a bit. Okay, so basically this lines of code, what it is doing, you can see this will display the obtained values of that coefficient. So, and best positions, yes, it will come here. Good. So now I will show just by running this. Yes, by pressing F5 we can run this simulation, and right now I ran it for 10 iteration and population number is having 10. Okay, we have got some error. Okay, so basically I think I typed mistake something. Okay, so it won't be like this. Okay, yes, I will run it once again. Okay, okay, I think I made a mistake here. Yes, now it's fine. Yes. Yes, so you can see here, basically we defined 5 variables. So means that 5 variables value obtained by GW is this one, and that like GWO-CS by this one, and these are the like their corresponding ISE value. But this is not looking good. So what I will do, I will try to represent in terms of transfer function so that it will be clearly visible to us. So for that, what I will do, I will just yes, what I will do, I will simply define that same transfer function whatever I've got here, this one. Okay, because this is the reduced system transfer function we need. Okay, so what I will do, I will simply write it here. Yes, and I will just remove this colon marks, semicolon, so that output will be visible to a screen. And here what I can do, you can write x is equal to this one, and this I did for like GWO. Similar thing we can do for GWO-CS. So GWO-CS, and this will is the position. Yes. Okay, and I think yes. Okay, so we can comment these lines, and I will show you. Yes. So this is the transfer function that we have got. Okay. It seems that GW is not here. Okay. Okay, fine. This and grid I will hide. Yes. So this is the transfer function. This transfer function is for that GWO first one, and this is for, but it's not clearly identifiable from this command window. So I will try to make some changes in this code so that it will be visible here, or else I will do one more thing, that means this should print at each iteration what is the values of that objective function. So for that, what we have to do, we have to make changes in this code like GWO-CS, right? And at last, up above this line, yes, this L is equal to L plus 1, I can write some code so that it will be like printed after each iteration, right? So this will be like something display, and here inside this square bracket I will write in that in this symbol we will write iteration number, and whatever you want you can write iteration number, and basically iteration number will be each iteration. So here L is being used for number of iteration. So here, and this is in terms of number. So first I will convert it into a string using num to str L, right? And after that, here I have to put that values. So values will be like ISE, or you can write best cost is equal to and here also means each iteration that should print the number. So number will be like this. Again I will use num2 str and that alpha score, alpha score. So this is our alpha score, right? So in this way it will print uh, this value after each iteration, right? So I will just cross verify by running it once. So yeah, good to go. It printed the values, but thing is that it started from okay, so I think there is some issue in this graph. Okay, but it started from 0. So just for that thing, what I will do, I will simply change this thing here from L plus 1, so that it will start from that thing and only, right? So yes, so you can see here this started from 1 2 3 4 up to 10, right? It's good. And okay, good. Now I will make changes just for displaying purpose, so that it will be clearly identified by any of the people whose system is like this. What is that, what is that, like thing just for simply some modification I will do. And what I will do, just write down here. Yeah, after that I want to display the ISE value for each display. And ISE value, ISE is equal to, in this quote, ISE is equal to, and better I will write ISE using GWO. GWO is equal to, and this comma num2 str, and this will be paste score, but not for CS. C. So same line I will copy for this also, and I will paste it here, and ISC GWO-CS, but here it should come CS. Good. And just to separate this, I will write one more command. Yes, I will put some these things inside just to separate, nothing else. Separate these lines. What I will do, just so that it will look good. Yes, perfect. So yeah, looks good. Okay, now I will run by just pressing F5. So you can see the values here. It is starting from 1. Good. So basically this is the iteration graph that we have got, and here you can see like it is starting from 1 to 10, and this is the G2, means basically I mean this is the transfer function obtained using GWO, and this is for GWO-CO. Okay, so I will make one more changes here. Better, that will be good. Simply GWO, and here you can write GWO-CS. Yes. So basically now I can run and show you. Okay, so this is the value GWO, means obtained for GWO. This is the transfer function and corresponding ISE value. For GWCS, this is the ISE value, and this is the transfer function. So finally this is done, means whatever the changes are required I showed you. And now what we can do, basically just by changing this iteration number or this search agent I mean population size, you can vary and you can get the optimal results according to that. And whenever you need to change, like this is for this system, so this transfer function you can change, and this according to your requirement. Suppose you need third order system, then what you have to do, just extend it up to x3, and here it will start from x4 by x5 x6 and up to x7 like this, and just change the number of variables here, I mean in dimension. Here you can change dimension 7 for third order system, right? So you can see this case switch cases we are not using, so we can delete this also, so that it will shorten the length of the code. So good. And except this F1, I can delete all the rest of the things, right? Yes, good. So I will run it once again and show you just by simply, yes. It will take some time because I changed the number of iteration in this. In this you can say we have got some good results, like from GWO we are getting that ISE value at 0.0015, and using that hybrid technique we are getting 0.0002, so it's good. And this can be interpreted from this graphs as well, that black line is more lower, I mean lesser than this red line value, so it's good. In that way, means this optimization working. So thank you for watching this video.